Dear students, I welcome you for the today's lecture related to the log mean temperature difference. In this, one is log mean temperature difference and second is the mean temperature difference. It is ultimately that we are using the mean temperature difference. For that, basically the flow patterns in the heat exchanger that are to be known. It is parallel flow, counter current flow and cross flow arrangements are available. Now, in case of a parallel flow arrangement, both the fluids move in the same direction. The hot fluid as well as the cold fluids, they move in the same direction. However, in case of a counter current flow heat exchangers, it is the movement of the hot fluid is in the opposite direction to that the movement of the cold fluid. So hot in and cold out, they are on one side, and hot out and cold in, they are on another side. So for that, I am going to plot a temperature profile diagram. How the variation of temperature that will be observed along the length of the heat exchanger. This is the length of heat exchanger, that is this distance. So whatever the temperature of a hot fluid, this is for the parallel flow arrangement. That means both the fluids, they are moving in the same direction. So hot in, which is the highest temperature, that is the THI. This is the highest temperature, that is hot fluid inlet temperature. And the lowest temperature is that of a cold fluid inlet temperature, that is TCI, is the cold fluid inlet temperature. Now on the another side, it will be the hot fluid outlet temperature and the cold fluid outlet temperature, TCO, that is the cold fluid outlet temperature. They are plotted along the distance L. So the hot fluid temperature that will gradually decrease and the cold fluid temperature that will gradually increase as they are going to exchange the heat. Similarly, in case of a counter current flow heat exchanger, both the fluids move in the opposite direction. However, the THI, which will be obviously the highest temperature, and TCI, which is obviously of the lowest temperature. So accordingly, the hot fluid will lose its heat and will attain a certain lower value of temperature. However, the cold fluid will increase its temperature and will attain a certain higher value more than this TCI. Now, writing this with the notations, that is parallel flow, THI, TCI, THO and TCO. So similarly, in case of counter flow heat exchanger, this is your THI and this is THO, that will be the same. But TCI is on this side and TCO is on the another side. Now, looking at these two curves, the heat transfer is because of the temperature difference. The motto in the heat transfer is the temperature gradient, is the temperature difference between the hot fluid and the cold fluid. So let us understand the temperature differences in this parallel flow arrangement and counter flow arrangement. So in this case of parallel flow arrangement, initially this is my temperature gradient. As the length of pipe progresses at initial stage, this is the maximum temperature gradient which can be observed. At the intermediate step, this is the temperature gradient that can be noted, and at the outlet it's the lowest temperature gradient which will be noted. So temperature delta T1, delta T2, and this is the average delta T that will be taken into account, and depending on this delta T, the value of Q that will be available, Q which is equal to UA delta T. So Q which is equal to the UA delta T. So this delta T that is going to vary, and accordingly the amount of heat transfer that is also going to vary. So for that purpose, in this figure also, that is the counter flow heat exchanger, the variation in the temperature difference that can be noted. However, in case of a parallel flow arrangement, at the inlet there is a maximum temperature difference, and at the outlet there is a minimum temperature difference. However, in the counter current flow exchanger, the differences in this temperature gradient is more or less nearly remains constant, not to that extent as varied in case of this parallel flow arrangement. So this is the temperature gradient which we can see. Now in these other figures also the temperature gradient that can be observed. Then the arithmetic average temperature difference may not be the real average temperature difference for the calculation of this Q value. So calculation of Q, that is amount of heat transfer, is going to be a very crucial, as this temperature difference is going to change. So the arithmetic average temperature difference, that is the delta TAM, which is nothing but the delta T1 on one side plus delta T2 on the another side. For that we are taking the average. But these values are not suitable to calculate the value of Q. They will give the error. This average arithmetic temperature difference values will give the error in the calculation of the Q, and for that purpose we are using the log mean temperature difference values. Now this log mean temperature difference values, that is delta TLM. Delta TLM is the log mean temperature difference, and it's a temperature gradient at one end minus temperature gradient at the another end upon ln of temperature gradient at the one end upon temperature gradient at the another end. So let us understand the temperature gradient from one end and on the another end also. The TCI and THI, first we will consider a case related to the parallel flow heat exchanger, where the inlet temperature for the hot fluid will be the highest and the inlet temperature for the cold fluid, that will be the minimum. So taking the temperature difference, that is delta T1, which is equal to the del TH in minus TC in, or THI minus TCI. This is one temperature difference, delta T1, and the second temperature difference, that is the delta T2, which is nothing but TH out minus TC out, that is delta T2, which is equal to TH out minus TC out. So temperature difference on one end minus the temperature difference on the another end upon the ratio of that temperature differences. So this is the delta TLM, that is log mean temperature difference. This is for what is the co-current flow arrangement. Now let us calculate it for the counter current flow arrangement. So in this case of the inlet temperature of the hot fluid, that is your THI, and the TCO, the temperature differences on one end, this is the delta T1, which is equal to TH in minus TC out, and the temperature difference on the another end, that is delta T2, which is equal to the TH out minus TC in. So this is the temperature gradient, you can say, on one end and at the another end. But the formula that remains the same. Only the temperature differences, they are different. So formula of delta TLM, which is equal to delta T1 minus delta T2 upon ln of delta T1 upon delta T2. Now the arithmetic mean temperature difference, which is calculated as delta TAM, which is equal to half the temperature differences on one end and the another end. The logarithmic mean temperature difference, delta TLM, is an exact representation of the average temperature difference between the hot and cold fluids. It is called the average temperature difference between the hot and cold fluids. That is what we are taking, the average of that temperature difference. And so what? We are calculating the log mean temperature difference, that gives the average of the temperature differences. So noting that delta T1 for the parallel flow heat exchangers, that is TH in, TC in, TH out, TC out, and here it is TH in, TC out minus TH out and TC in. The difference is to be remembered. Instead of that, it is better to plot a graph and take the averages of that. Now there are certain situations where the values for the temperature that doesn't change. They are your condensation and the boiling processes. In case of a condensation, that is generally carried out at a constant temperature, only the phase change that is noted. And when it's a constant temperature, there we have to consider the condensing fluid, which will be having a constant or a straight line where the temperature gradient is not. Temperature gradient is not available for the hot fluid. So it's a condensing fluid will have a straight line. And in case of a boiling fluid, the process of a constant temperature, only the phase change that is observed. So whenever there is a boiling that is taking place, it is the constant temperature that will be noted. However, the hot fluid, which is going to decrease its temperature, and in case of condensation, cold fluid, which is going to increase its temperature. So delta Tm is an appropriate mean temperature difference between the two fluids. Here also you can observe that the variation in the temperature gradient that is drastically reducing. So in this, the limiting case of a cold fluid, okay. So finally, Q, which is equal to UA delta Tm, where delta Tm is the true temperature difference or the mean temperature difference, and which is calculated as delta Tm, which is equal to Ft delta Lm, where delta TLm is the log mean temperature difference. You have to understand this delta Tm and the delta TLm. It is the true temperature difference or the mean temperature difference, and second one is the log mean temperature difference, where Ft is the correction factor. Now where this will be applicable? It is applicable in case of your heat exchangers, because in the heat exchanger generally it's a cross flow that is observed, and when there are number of passes, they are going to change. Now consider a case of a shell and tube heat exchanger where there are two passes on the tube side. This is the tube side fluid out and tube side fluid in. So tube side fluid that is entering in the shell in the tube, and it changes its path, and to the same fluid which is on the shell side, it is going out through the tubes. Now if we will plot this with a temperature profile, the shell side fluid, which is considered to be the hot in this case, that is THI and THO, it will be the same thing, similar to our previous temperature profile diagram. However, in case of a cold fluid, the TCI that will gradually increase, will reach to the another end and will change its path, its direction, and will go out on the same path. So what is to be done in these situations is becomes a critical, and that is why we are considering delta Tm as the mean temperature difference, and it is calculated by using the delta TLm log mean temperature difference. In such situations, we will be plotting a graph in a counter current operation. A counter current operation will plot a graph where is in this direction and the cold fluid will move in this direction, and we'll take a temperature gradients on this side and the temperature gradient on this side. So we will calculate the log mean temperature difference, and we will use this correction factor F, or sometimes it is FT correction factor. So F is a common cross flow arrangement. F is taken for the cross flow arrangement, where P and R, or S and R, they are calculated by using the temperature differences, where T2 and T1, they are the inlet and outlet, and capital T and small t, they are on the shell and tube side. That is what? The shell side. They are not mentioned specifically whether it's a hot fluid or cold fluid. That may vary. So it's a shell side and tube side. Or other way, TH hot in minus THO upon TCO minus TCI. So the calculating the value of R and the value of S, that is, this factor is same as the denominator of this factor, that is TCO minus TCI. Here also TCO minus TCI. Now the temperature difference for the R, that will be calculated for THO minus THI, and in this case THI minus TCI. And by using these values of R and S, I will be able to calculate the value of correction factor by considering this formula. That is one option. There is also a second option, to refer to the graphs which are standard available to calculate the correction factor. Now it depends on the number of passes, that is the T1 and T2, which is outside. So T1, it's a 2 pass on the tube side. Now this is the second figure relating to the 4 passes on the tube side. So this is 1 shell pass and 2, 4, 6, etc. tube passes. Then I am going to use such graph. Then for 2 shell passes, here it's was 1 shell pass, here it is 2 shell pass. The difference, shell side also there are number of passes, tube side also there are number of passes. So the difference lies there depending on how many number of passes for the shell side and for the tube side. I have to select a proper graph. So all these graphs, they are representing the correction factor values on the y-axis. R values are there and these are S or P values. So graph is plotted between the factor S, correction factor F and the S values. And for that, for the different values of the R, I will get a curve like this. So all these graphs are similar to this. Correction factor F against the P or S values for the different values of the R. So by calculating the values of the R and S and referring to a typical or particular graph, I can calculate the value of this correction factor. So these are the single pass cross flow with both fluids are mixed, then single pass cross flow with one fluid mixed and the other unmixed. So that is the different permutations and combinations are available. Now, this calculation of log mean temperature difference is very suitable for determining the size of heat exchanger. That means in the designing procedure of a heat exchanger, you require the calculations of this log mean temperature difference, and that is of most importance. You have to remember that the true temperature difference or the mean temperature difference, which is equal to Ft into delta TLM, that is the log mean temperature difference. And when this will be applicable, that will be applicable when there are more number of passes, or else delta Tm will be is equal to delta TLM.